next of our videos looking at advanced higher physics past papers, and as usual we're going to the Calder Glen High School website. We're clicking on advanced higher physics and then past papers. When that opens up, the first link you see is to Mr. Davies' fabulous interactive PDF of past papers by key area, and when you open that, that'll take you to a little document where you can click on the individual key areas, and if you click on the individual questions, they will open with the solutions as well. So in this one we're going to have a look at magnetic fields, and we're firstly going to look at the 2016 paper. We're going to look at question 14, and then we'll look at the 2022 paper, question 15. And as usual, have a go at the question first, and then when you're ready come back and we will show you how we have done it. So 2016, first thing you see as usual is the data sheet, and the constant that you're probably going to be using in magnetic field questions is the permeability of free space mu naught, and it's given on the data sheet as 4 pi times 10 to the minus 7. In fact, it's the only constant on the data sheet that's given as a multiple of pi, and it's pretty tricky to put into your calculator. You've actually got to put it in as 4 pi times 1 times 10 to the minus 7. But you might not even have to do that, but we'll see that when we go through these two questions. So, 2016, let's have a look at question 14. A student measures the magnetic induction at a distance r from a long straight current carrying wire using the apparatus shown in figure 14. So we've got a magnetic sensor there, and it's measuring the size of the magnetic field, if you like, at a distance from that current carrying wire. And the measurements are given below, so the following data is obtained. The distance from the wire r is 0.10 metres, and the magnetic induction B is 5.0 microtesla. And we have to use the data to calculate the current I in the wire. So it's a calculate question, 3 marks, so we should go straight to our relationship sheet. And if you're looking for one, then you'll find one on the Calder Glen High School website. If you go to the advanced higher page and click on the bottom link there, there's useful documents and websites, and the top one there is the 2023 version of the relationship sheet. And you'll also get a data sheet there, the full course specification from the SQA, and a link to this YouTube channel. Anyway, let's open up the relationship sheet, and on page 3 you'll see all the magnetic field equations. That's the equations with B in it. There's 3 of them there on the right hand side, and the one that we are looking for just now is B equals mu naught I over 2 pi r. So let's write that down, and we have to calculate the current in the wire. So it's good practice to substitute everything in first. So mu naught is 4 pi times 10 to the minus 7 times I divided by 2 pi times the distance from the wire, which was 0.1 metres. Now I said there was a wee trick you could do here, because typing 4 pi times 10 to the minus 7 into your calculator is pretty tricky. It's a bit of a faff. You've got to type 4 pi times 1 times 10 to the minus 7. But the way around that is just to do 4 pi divided by 2 pi, and that leaves you with 2 times 10 to the minus 7 on the top line, times I divided by, in this case, 0.1. Then we can rearrange it for I, so I will be equal to, let's see here, well, the magnetic induction was 5 times 10 to the minus 6 times 0.1 divided by 2 times 10 to the minus 7. And if you do that on your calculator, you'll get an answer of 2.5 amps. Let's have a look at the SQA marking instructions. 14 part A, there it is, standard 3 marker, 1 for the equation, 1 for the substitutions, and 1 for the final answer with the correct unit. Now, the rest of this question is really uncertainties. Part A was the only bit that was about magnetic fields. The rest of it is really about the uncertainties in the measurements that were made during the experiment. So part B, the student estimates the following uncertainties in the measurements of B and R. And we've got a table that's got the scale reading uncertainty in the measurement of R, and the calibration uncertainty in the equipment that was used to measure the distance R. And we've got the same for the uncertainties in B as well. And firstly then we have to calculate the percentage uncertainty in the measurement of R. Now remember, that was the distance from the magnetic sensor to the current carrying conductor, and we were given that it was 0.10 metres. So that's the measurement we're interested in for this part. So let's write that down again. The distance was 0.10 metres, and the scale reading uncertainty in that is plus or minus 0.002 metres. So we can work out what that is as a percentage of the measurement. So it'll be 0.002 divided by 0.10 times 100, and when you do that in your calculator you'll get 2%. And then we can do the same again with the calibration uncertainty. It's plus or minus 0.0005, and if you work out what that is as a percentage of the measurement of 0.10 metres, then that gives you an answer of 0.5%. Now we've got a rule here when we're dealing with uncertainties, and that rule is that if one of your uncertainties is less than a third of the other ones, then you can ignore it. So we're going to ignore the 0.5%, so the percentage uncertainty in the measurement of R is 2%. That's a lot of work for 1 mark. In B part 2, what's the percentage uncertainty in the measurement of B? Now our measurement of the magnetic induction was 5 microtesla. So let's jot that down again, and then do the same thing that we did in the previous part of the question. So the scale reading uncertainty was plus or minus 0.1 microtesla. So what's that as a percentage of the measurement of B? So the scale reading uncertainty is plus or minus 0.1 microtesla, and if you work out what that is as a percentage, then that's 2%. And if we look at the calibration uncertainty from the table, then we're told that it's 1.5% of the reading. So we don't have to work that out, it's 1.5%. But if we look at both of these two percentage uncertainties are similar in size. So what we should do with them is we should combine those uncertainties. And the way that you do that is you square them, you add them together, and then you take the square root of it. And if you do that on your calculator, you'll get an answer of 2.5%. And if you're looking for the relationship to do combinations of percentage uncertainties, then they're on the bottom of page 3 on your relationship sheet. You've got a choice of 2 there. I always use the kind of simpler version, but always use percentage uncertainties in that calculation. The second relationship is where you would sub in the uncertainty divided by the measurement itself. It's a bit more clunky, but you'll get the same answer. If we look at the SQA marking instructions for this, it's B part 2. Then it's 1 mark for the scale reading uncertainty as a percentage is 2%. 1 mark for the relationship for combining the percentage uncertainties, and 1 mark for the final answer. We don't really like uncertainties. Anyway, 14b part 3, calculate the absolute uncertainty and the value of the current in the wire. Right, we calculated the current from the relationship, and we got a current of 2.5 amps. But in that relationship, it was B equals mu naught I divided by 2 pi R. And we've got the measurements of B and R in that relationship that we used to work out I. Now the percentage uncertainty in B was 2.5%. The percentage uncertainty in R was 2%. So again, we are going to have to combine both of them to get the percentage uncertainty in I. And from that percentage uncertainty, we can work out the absolute uncertainty and the value of the current. Phew, what a lot of work. So again, we're using the Pythagorean method, where we took our percentage uncertainties, we're going to square them, add them together, and then square root them. That gives you an answer of root 10.25. Now you could leave that like that, so your current, which was 2.5 amps, will be plus or minus root 10.25%. Let's work it out though, that's 3.2%. So the uncertainty is 3.2%, and 3.2% of 2.5 is 0.08 amps. That's a monster. But bear in mind, the projects are now back and you should have had a bit of experience at dealing with your uncertainties and combining them. Okay, part C. The student measures distance R as shown in figure 14 using a meter stick. Smallest scale division on the meter stick is 1 millimetre, And we have to suggest a reason why the student's estimate of the reading uncertainty in R is not plus or minus half a millimetre. Well, usually we would say that the scale reading uncertainty is plus or minus half the smallest scale division on the measuring equipment. But if we look at the diagram of the apparatus here, we've got the magnetic sensor and we've got the current carrying wire, and that measurement of R would be very difficult to make to within half a millimetre, because it's difficult to tell where the centre of the magnetic sensor is and where the centre of the wire is. So let's put that in as our answer. Difficult to locate the centre of the wire and the centre of the magnetic sensor. There's our SQA marking instructions then. For part 3, it was 1 mark for the combination of the percentage uncertainties and 1 mark for working out the absolute uncertainty. And then in part C, it's the uncertainty in measuring the exact distance from the wire to the position of the sensor. Tricky question because it was mostly uncertainties. But let's have a look at another one then. The 2022 paper, hopefully this will be a bit more straightforward. And it's question 15. An undersea high voltage DC electrical power link consists of 2 cables buried under the seabed, and the magnetic permeability of the seabed can be taken to be the same as the permeability of free space. That's the mu0 constant that's on your datasheet. And there's a current of 1.80 kiloamps in each cable, and the cables are buried 30.0 metres apart, as shown in figure 15a. Interesting diagram. And we have to calculate the magnetic induction at cable 2 due to the current in cable 1. So back to our relationship sheet again, and B equals mu0 I over 2 pi r. And it's B we're looking for, so let's substitute everything else in. Mu0 from the datasheet is 4 pi times 10 to the minus 7. The current, and be careful here, it's 1.8 kiloamps, that's 1.8 times 10 to the 3, and that's divided by 2 pi r, where r you would think would be the radius. It is, it's the radius at which the magnetic field extends to, but in this case that's the distance, and that's 30 metres. And again we can do the little trick here of cancelling out 4 pi with 2 pi, that leaves us with 2 times 10 to the minus 7 times 1.8 times 10 to the 3 divided by 30. And if you do that on your calculator, that gives you an answer of 1.2 times 10 to the minus 5 Tesla. Okay, moving on. Part 2. Determine the magnitude of the force per unit length, that's in bold, acting on cable 2 due to the current in cable 1. The force per unit length, well, the unit length is 1 metre. So have we got a relationship that links force with current and length and magnetic induction? Yes, we do. F equals ILB. Now we know what the current in cable 1 is. It was 1.8 kiloamps. So it's 1.8 times 10 to the 3. So if we put in a length of 1 metre there as well, and the magnetic induction, which we calculated in the previous part of the question, and it was 1.2 times 10 to the minus 5 Tesla, then that gives us an answer for the force per unit length acting on cable 2 of 2.2 times 10 to the minus 2 newtons, or 0.022 newtons. That's quite tricky. Let's have a look at the marking instructions for those first 2 bits. So part 1, there's our answer of 1.2 times 10 to the minus 5 Tesla. That's a standard 3 marker. And for part 2, we're using F equals ILB to get the force per unit length. So we're substituting in the length of 1 metre to get a force per unit length of 2.2 times 10 to the minus 2 newtons per metre. Notice the units there, newtons per metre. But on the right hand side, it says where L is substituted as 1, accept the final answer in newtons. That was the way I did it. But both of them acceptable there. Okay, 15 part B. A third cable carries a fibre optic link, and the fibre optic link is made of silicon dioxide. And the speed Vm of an electromagnetic wave in an optical fibre is given by the relationship And then we've got this relationship which we've never seen before, although there is something similar to it on your relationship sheet. But this is one of these unfamiliar relationship questions. And in this sort of question, all you're doing is substituting in the data that you're given, plus also some data from the data sheet to find out the quantity that you're asked. So what are we asked to find here? We've to determine the relative permittivity of silicon dioxide. Now there's loads of symbols in that relationship. We know Vm is the speed of the wave in the material, E naught's on your data sheet and mu naught is on your data sheet. That's the permittivity of free space and the permeability of free space. Now ER is the relative permittivity of the optical fibre material. That's the one that we've to find. And we know what the speed is, it's 1.52 times 10 to the 8. And we're told the relative permeability of silicon dioxide is 1. That's the mu subscript r value. So the quantity we're looking for is E subscript r, or epsilon subscript r, the relative permittivity of the optical fibre material, in this case silicon dioxide. So we're just going to sub in all the numbers that were given. The speed, 1.52 times 10 to the 8, is equal to 1 over the square root of E subscript r times the permittivity of free space, 8.85 times 10 to the minus 12, times 1 is the relative permeability of silicon dioxide, times the permeability of free space, 4 pi times 10 to the minus 7. And then we're going to rearrange that and try and find E subscript r. And the way to do that is to square both sides. That will get rid of the square root sign on the bottom on the right hand side. And then rearrange it for the relative permittivity of silicon dioxide. That's epsilon subscript r, or E subscript r. That will be equal to 1 divided by 1.52 times 10 to the 8 squared, because remember we squared both sides, times 8.85 times 10 to the minus 12 times 4 pi times 10 to the minus 7. And if you do that carefully on your calculator, you'll get an answer of 3.89. Now, what about units? Well, it's the relative permittivity, and if you look at the relative permeability of silicon dioxide, it's 1 with no units. So in other words, it's the same as the permeability of free space. So the relative permittivity of silicon dioxide has no units. It's just 3.89 times bigger than the permittivity of free space. And notice on the right hand side of the answers, it says that if a unit is given in the final answer, you're only going to get 1 mark for your substitutions if you've done them correctly. Again, pretty tricky. That's it for this video then. I suppose the lesson is don't mix up your E naughts and your mu naughts. Next time, we're going to stay with fields, but we're going to look at uniform electric and magnetic fields. See you in the next one.